Hello everyone. Today we are back with another type of unsupervised machine learning, which is dimension reduction. If you follow this video till end, then you should know how the dimension reduction works. What are the different type of algorithms in dimension reduction? And you should be able to build any type of model in dimension reduction with any type of algorithms. So before we start, here are a few details about DataMonk. In DataMonk, we help students to prepare for different type of interview and also provide study material in SQL, Python, R, statistics, case studies, and machine learning. If you want to know more about the DataMonk, then you can visit our website www.thedatamonk.com. So let us start with the unsupervised machine learning. So first of all, what do you mean by unsupervised machine learning? As we have already discussed the supervised machine learning. In supervised machine learning, we have a input and the output, and we have to predict the output. But in unsupervised machine learning, we do not have the output. In this, we do not have to explicitly train our data by telling this that this is the input and this is the output. In unsupervised machine learning, it is about finding the pattern in the data just by passing full data to the algorithm. So there are three major type of unsupervised machine learning algorithms. They are clustering, dimension reduction, and association. We have already made a video on the clustering. So today we will discuss about the dimension reduction. So what do you mean by dimension reduction first of all? In dimension reduction, it is about finding and combining similar columns in our data. Basically, reducing the number of columns to the lower number of columns. There are some important algorithms used in dimension reduction like factor analysis, PCA, ICA, TSNA, and UMAP. So in this video, we will discuss the working of all these five type of dimension reduction and then build the model in all these five type of algorithm. So let us start with dimension reduction. So for the definition of the dimension reduction, first we will know what do you mean by dimension or dimensionality. So the number of input variable or feature for our dataset is referred as a dimensionality or dimension. Dimensionality reduction refers to a technique that reduces the number of input variable in a dataset. More important feature often make a predictive model task more challenging to models. So basically, it is also known as a curse of dimensionality. The high dimensionality statistic or dimensionality reduction technique are often used for data visualization. Nevertheless, this technique can be used in applied machine learning to simplify a classification or a regression dataset in order to better fit a predictive model. So now you understand what do you mean by dimension reduction. So we will look into different type of algorithms in the dimension reduction. So our first algorithm for dimension reduction is the factor analysis. So factor analysis is one of the most popular algorithm in dimension reduction apart from the PCA. So for factor analysis, it is a dimension reduction technique. The goal is to find out latent factor or hidden groups that are responsible for the observed data in the variables. Let us take one example. Like if an employee is unhappy in an organization, there could be many reasons for it. But if you look carefully, these reasons can be grouped together within some smaller set of major reasons. The factor analysis help us to find this major group of variable in the data which are known as our factors. So let us look at the diagram below. It represents from a data of an employee survey. It shows the average rating for each department, like how employees feel about the way their employer handles the complaint, or how they feel about the privileges provided, or how they feel about the learning on the job, or how they feel about the salary and career advancement. So as you can see, we have seven columns: rating, complaint, privileges, learning, raises, critical, and advanced. So you can see some of these responses represent a common subject or the major reason for the way they responded. Like if they are satisfied with their organization work culture, then the score will be high for overall rating, complaints, and privilege. And if they feel they are learning on the job, then score will be high in learning opportunity, similar for the promotion. So there are three major reasons: work culture, learning opportunity, and promotion, which actually drive the rating of smaller reasons like rating, complaint, privilege, learning, and etc. So as you can see, we can combine this column into group 1, which is work culture, this column into group 2, which is learning opportunity, and this column into group 3, which is promotion. So statistically, we can imagine the equation of the above diagram as below. So for rating, we can give as beta 1 into work culture plus C1, and for complaint, beta 2 into work culture plus C2, as they are the group of the work culture. Same for the privilege, beta 3 into work culture plus C3, and for learning, beta 4 into learning opportunity plus C4, and for raises, beta 5 into promotion plus C5. So basically, factor analysis help us to find the value of beta 1 C1, beta 2 C2, beta 3 C3, and all the beta and the C values. So this coefficient determines that what is the weightage of rating complaint privilege in our work culture factor, what is the weightage of raises critical advance in our promotion factor. So this weightage like beta 1 and C1 are also known as our factor loading. Basically, what part of a given variable contribute to the group of factor it belongs to. So that's the working of the factor analysis. And now we will look into the principal component analysis, also known as PCA. In simple words, PCA is a method of extracting important variable in form of components from a large set of variables available in a dataset. It extracts low-dimensional set of features from high-dimensional dataset with a motive to capture as much information as possible. With fewer variables, visualization also become much more meaningful. PCA is more useful when dealing with high dimensional data, like more than 20 columns. So now we will look into what do you mean by principal component in our principal component analysis. So for principal component, it is a normalized linear combination of the original predictor in our dataset. So let's see the working of our principal component analysis. So let's say we have a set of predictor like x1, x2, x3, x4, x5 until xp. So first principal component can be written as z1 equal to alpha 1 into x1 plus alpha 2 into x2 plus alpha 3 into x3 and so on till alpha p into xp. The first principal component is a linear combination of original predictor variables which capture the maximum variance in the dataset. It determines the direction of highest variability in our data. Larger the variability captured in first component, the larger the information captured by the component. No other component can have variability higher than the first principal component. The first principal component results in a line which is closest to the data. Like for example, it minimizes the sum of square distance between the data point and the line. Similarly, we can compute the second, third, fourth principal component with same formula for linear combination. So now let's look into the image to see the working of the PCA. So as you can see, this is our original data, which has rating, complaint, privilege, learning, raises, critical, and advances. So we can use PCA to reduce the dimension in our data set. So we have used the PCA and we have reduced it to only 4 dimensions. So as you can see, this is our principal component and this is our original data. So how did we calculate this value from this? So as we have already discussed that like this value will be equal to the alpha 1 of this plus alpha 2 into this plus alpha 3 into this plus alpha 4 into this plus alpha 5 into this plus alpha 6 into this and plus alpha 7 into this. So in principal component, we just have to calculate the value of the alphas. So after calculating the value of the alphas, we can easily calculate our this value. So this step will only work further and deduct the value of all these columns. So as we have discussed the working of our PCA, like alpha 1 into rating plus alpha 2 into complaints and all that. So from this we can find the linear combination of our variable in the data. And another point for the working of our PCA is that while satisfying the independence criteria for all principal components, if we pick any two principal components and find the correlation between them, it should be zero. Like if we pick this column and find the correlation between them, then it will result into zero as they all will be the independent values. And the another point for the PCA is that the first principal component explains the maximum amount of variance in our data. Second principal component explains slightly less amount of variance and so on and so forth. So now you are familiar with the working of the PCA, but how can we differ PCA with the factor analysis? So factor analysis is often confused with the PCA principal component analysis. Both are dimension reduction techniques, but the main difference between the factor analysis and PCA is the way they try to reduce the dimension. So for factor analysis, factor analysis try to find the hidden group of variable, which is like a common driving factor for the type of values in all these variables. For example, for the customer survey, if you are unhappy with the taste of the coffee, then all those questions about the coffee taste in the survey will have low score. Hence, bad taste will be a factor, and questions like coffee sweetness rating, coffee bitterness rating, coffee freshness rating will represent the individual variable that will have the low rating. So the equation for the factor analysis in this will be for coffee bitterness rating, it will be beta 1 into bad test plus C1. Same for coffee bitterness rating, it will be beta 2 into bad test plus C2 and so on. But in PCA tried to find fewer new variables called principal component which are linear combination of the variable in the data. Hence, this fewer variable represent all the variable while reducing the dimension. Here, our goal is to create the new dataset that has same number of rows but lesser number of columns or principal component which explain the variance of all the original variable in our data. So in this, our equation will be formed like PC1 equal to alpha 1 into coffee sweetness rating plus alpha 2 into coffee bitterness rating plus alpha 3 into coffee bitterness rating. And same for PC2, it will be beta 1 into coffee sweetness rating, beta 2 into coffee bitterness rating plus beta 3 into coffee freshness rating. So and so on till we capture all the variants in our dataset. So now you should be able to differentiate between factor analysis and PC and should know the working of both the algorithms. So we will move forward and discuss about the independent component analysis, which is also known as ICA. So for independent component analysis, the algorithm is very similar to the PCA, but there is a very subtle difference. In PCA, we try to find the linear combination of variable as principal component, and there is no correlation between the principal component. But in ICA, we try to find the linear combination of variable as independent component and there is no dependency between any two components. So now you should be wondering what do you mean by correlation and the independence. So for correlation signifies the mathematical relation between two vectors like sale increase with an increase in discount and hence there is a high positive correlation. But the actual driver of sale would be the quality score of the product. Hence, we can say that sales are dependent on the quality score of the product. Similarly, independence is also defined like sale of the shampoo is independent to the weather, but sale of the ice cream is dependent on the weather. So now let us look at the mathematical equation of the ECA and see the working of the ECA. So in ECA, we establish an equation x equal to m into d, where our x is the matrix of the independent component, m is the mixing matrix, and d is our original data. So let us look into the formula. So as you can see in the formula, we want independent component x, which we will get by multiplying between the mixing matrix and the original data. And the goal of the ICA is to find a matrix of mix, which is m, to be multiplied by the given data d, such that all the columns in x are independent of each other. So now you should know what do you mean by ICA. So now we will look into our next algorithm, which is TSNA, also mean by T-distributed stochastic neighbor embedding. Don't get nervous with the name, it is actually very simple. This is just the another dimensionality reduction problem, primarily aiming at visualizing the data. Since plotting of high dimensional data is computationally intense as well as difficult to understand. So if the data can be represented in these 2 or 3 dimensions, then it can be plotted very easily and the data pattern can be understood. This can also be done using the PCA, but it is a linear method. If the relation between the features are non-linear, then PCA will surely fail to provide good components that are efficient in explaining the variance. This is where our TSNA comes into the picture. So for TSNA can find the non-linear relationship between feature and represent them in a lower dimension. So basically, it reduces the high dimensional data to the 2 or 3 dimensions. And TSNE works by finding the probability distribution in low dimensional space, similar to the distribution of original high dimension data. So now we will see the working steps of the TSNE. So for TSNE, first we will find the Euclidean distance of every point from every other point in the data of high dimension. Then after that, we will calculate the probability of 2 points being close to each other in the high dimension. And if the distance is very low, then the probability will be high. So similarly, we will find the Euclidean distance for every point from every other point in the data in low dimension and then calculate the probability of 2 points being close to each other in low dimension, and if the distance is low, then the probability will be high. So we will minimize the difference in probability of high dimension to the low dimension. So let us look into the figure to explain it in more better way. So as you can see, our t distribution has long tails as compared to the normal distribution. So this is our normal distribution, and this is our t distribution, which is more flat but have a long tails as compared to the normal distribution. The t in the TSNE is the t distribution, like this is the t distribution curve, and the reason for using the t distribution instead of the normal distribution is the long tail of t distribution, which allows the representation of long distances in a better way. And for SNE in TSNE, it is just the stochastic neighbor embedding, which means that this concept try to keep the cluster of data points in higher dimension intact with each other when these data points are encoded in the lower dimensions. Then after that we will discuss our last algorithm, which is uniform manifold approximation and projection, also known as UMAP. So for UMAP, it is just the improvisation of our TSNE algorithm. The basic concept will be the same, projecting the higher dimension data into the lower dimension. But the two noteworthy points regarding the UMAP are that UMAP is faster than our TSNE. The algorithm is less computationally intense, hence it can handle very large dataset. And the last point is that UMAP uses an approach like our k nearest neighbor to preserve the local and the global patterns in our data. The points which are close in the high dimension data will be close in the low dimension data as well, and vice versa. To perform this activity, the UMAP algorithm need two hyperparameters. One is n neighbor and second is minimum distance. So for n neighbor, it tells us that how many near points we should look for. And for minimum distance, it tells us that what should be the minimum distance between the points so that they are considered as our neighbor. Using the above parameter n neighbor and minimum distance, the UMAP algorithm finds out a relative position for each point in the lower dimension while keeping the relative distance of all points the same, hence representing our high dimension pattern. So now you should know the working for all the algorithms in our dimension reduction, like how they work and what are the differences between them. So now we will build our model from scratch and see the code for all the algorithms. So for the model, we have taken the office data that we have used in the example of above algorithms. So our problem statement is to reduce the dimension of the office dataset. So to build any model, first we will explore our data. And to explore our data, we have imported library pandas SPD. Then after importing the library, this is our data. Like this is our first column, rating, second column, complaint, then privilege, then learning, then raises, then critical, then advanced. So from this data, first we will form our data frame. And to form our data frame, we have used the list and the zip. Zip will combine our all the columns, rating, complaint, privilege, and others, and list will create that into the tuple. So after zipping the data and creating the list of the tuple, we will print our tuples. So this is what our tuple look like. So our next step is to convert this list of tuples into our data frame. So we use pd.dataframe to convert our list of tuples, and we have named our columns as rating, complaints, privilege, learning, raises, critical, and advanced. Then we have printed our data head. So this is what our data look like, and we will work on this data frame in further algorithms. So first we will see how to write the code for the factor analysis in the Python. So to write the code for the factor analysis in Python, first you have to install the required library, which is pip install factor analyzer. So after installing our factor analyzer library, then we have built our model. So to build our model, first we have imported factor analyzer from our factor analyzer library. Then after that, we have created our model from this line, fa equal to factor analyzer. Then after creating our model, we have to fit our data into our model. So we have used the fa.fit for fitting our data. So we have fitted our data into the factors. After that, we will plot our scree plot. So what do you mean by scree plot? Scree plot tells us that how many factor or a dimension we should form for our good model. So after plotting the scree plot, this is what our scree plot look like. So from the scree plot, we will take that point from where our line is getting straight. So looking into this plot, we can see that at the point 4, our line is getting straight. Therefore, we will take 4 as our plot number, and we will make 4 factors out of all the columns. So now we are creating 4 factors based on this scree plot. So after that, to create our model, we have two hyperparameter. First is n component, and then second is random set. And for n component, it means that we'll make four columns. And for random set, it means that we are picking random data from our dataset to form the columns. So after assigning the values to the hyperparameter, we will fit our data into the factors. Then after that, we'll print our factor loadings. So this is our factor loadings. Like this is our first column, this is our second column, this is our third column, and this is our fourth column. And these are the factor loading for each columns. Like PCA1 for rating is 5.96, PC1 for complaint is 8.16, and PC1 for privilege is 11.88, and so on. So now you should be able to write the code for the factor analysis. So now we will see how to run the PCA, principal component analysis, in the Python. So to run the PCA in Python, first we have to import our PCA from the decomposition. Then after importing the library, we will build our model. So from this statement, we have built our model PCA bracket n component equal to x dot shape by 1. So this assigns the number of columns in our original data set to the n component, and then we have created our PCA. Then after creating our model, we will fit our data using the x in our principal component. So after that, we will find the variance explained by each component. And to find the variance explained by each component, we have used the principal component dot explained variance ratio, and then add all the explained variance ratio to our variance explained cumulative, and then plot the graph for the variance explained cumulative. So why we have plotted this graph? We have plotted this graph to find the optimum number of component. So from this, as you can see, this is our graph. So as you can see, from point 5, our line is getting straight. Therefore, by looking at the graph, we can see that 5 components are explaining maximum variance. So for this, we have choose the n component as equal to 5, and then created our model. Then after creating our model, we will fit the data into our model. So from this, we have fit our data into the model. Then we will understand the factor loading on each columns. So as you can see, this is the factor loading on each column. So like this is our factor loading for the first column, like PC1 and the rating, and this is for PC1 and the complaint, and so on. Same as PC2 and rating, and PC2 as complaint. And you can see there are 5 principal component, as we have created our 5 principal component from the graph. Then after that, we will convert this factor loading into our data frame. So to convert this factor loading into our data frame, we again use the pd.data frame and assign the value to the final PC, and then printed the head of our final PC. So this is the head of the final PC. So this is our component PC1, PC2, PC3, PC4, and PC5. So from this, you can also see that in PC1 there will be highest variance than the PC2. Then and in PC2 there will be a higher variance than from PC3, and so on. As PC1 explain the highest variance in our dataset. Then after seeing the code for the PCA, we will see how to run ICA in our Python. So to run ICA in our Python, so we have to import one library which is fast ICA from sklearn.decomposition. So after importing the library, we will build our model ICA equal to fast ICA, where our n component is 2. And in this n component, we can give n component equal to 3 or n component equal to 4, depending on our choice how many final independent component we want. Then after assigning the n component value, we will fit our data into the model. So we have fitted our data into the independent component values, and then afterward we have created the data frame for the independent component value. So in this, you can see we have created our data frame, and the data is for independent component value, and there are only 2 columns as our n component was 2. So IC1 and IC2. So this is the head of our data, where we have reduced our full data into only 2 columns, IC1 and IC2, and they both are our independent component. Then after building the model for the ICA, we will see how to run tsne in our Python. So for tsne, first we have to import the library, import tsne from our sklearn.manifold. Then after importing the library for the hyperparameter n component, we have assigned it to 2. That means that we will reduce the original data into the 2 dimension using the tsne. And the basic function for tsne is to visualize the data. So it will be easy to visualize the data in 2 dimension or 3 dimension. So that's why we have used n component equal to 2. Then after sending the value to the hyperparameter, we will fit our data x into our component value. Then after fitting the data, our model has been created. So we will directly create the data frame for our component value. And you can see we are creating our data frame. So pd dot data frame, and our data is component value, and columns are comp1 and comp2 as our n component equal to 2. Then after that we have printed the head of our data. So this is the head of our data. Then after printing the head of our data, we will visualize the data in two dimension, as the main function of the tsna is to visualize the data. So as you can see, this is the visualization of our data. So in this, they all are our data points, and we have reduced our data into two dimension, which are in y-axis and x-axis, and then we are able to visualize the data. So after seeing the code for the tsne, we will see how to run UMAP in our Python. So to learn our UMAP in our Python, first we have to install the library. And to install our library, we have to write the code pip install umap-learn. So after installing our umap-learn, we will import our libraries. So we have imported UMAP. Then after that, we will assign the value to our hyperparameter. As we have already seen, our hyperparameter for UMAP, which are n neighbors, minimum distance, and n component. So for n neighbor, it tells us that how many near points we should look for. And for minimum distance, it tells us that what should be the minimum distance between points so that they are considered as our neighbors. And for n component, it tells us that how many columns we should form after reducing our data. So after assigning the hyperparameter for our UMAP model, we will fit our data into our UMAP model. So after fitting the data, we will directly create our data frame. So from this line, we have created our data frame, pd.data frame. This is our data equal to component value. And these are two columns, as you can see in our n component equal to 2, and also basic function of UMAP and TSNE is to visualize the data. And to visualize the data, we again need two or three dimensions. So in this, we have used the two dimensions. So after that, you can see the head of our reduced data. We have reduced all the columns to our two component comp1 and comp2, and this is the first 10 data of our data set. So that's all for the dimension reduction. Now after this video, you should be able to build any model in our dimension reduction, and also know the algorithm for our dimension reduction algorithms. So thank you for your time. Hope you like the video. For more amazing video and algorithm video, do like and share the video.